A very good morning to all of you. My name is Dr. S.S. Malik, and today we are going to talk about a very relevant and a necessary topic, which is how to increase the pneumatic ash handling rate in thermal power plants. Now, we are standing in an era where the environmental concerns, environmental pollution, as well as water conservation is becoming an issue of global worry, I would say, in a big way. And our country is no exception. In the recent years, the government has been very proactively pushing these agendas that we cannot use ash in the form of slurry. At least we should try to minimize it as much as possible. And one very common sense way of doing that is if we can, instead of using slurry for fly ash, if we can use our dry pneumatic ash handling system for conveying fly ash, if we can run it with full capacity, then that issue of water consumption to dispose ash to the ponds, that will be automatically taken care of. At the same time, while water is scarcity, at the same time, land is also a scarcity. And getting such large ash dike area is something which is not encouraged these days. And we can all understand the reason behind the same. With such constraints, we have to work on. We cannot stop our power stations because our country needs a tremendous amount of electricity to meet with the increasing demands or the forecasted demands which are going to come up. So what to do? So the way to go ahead would be, or one of the way to go ahead would be to revamp our existing ash handling capacities wherever there is a shortfall of the pneumatic ash handling system, dry conveying system. We need to revamp that so that our dike area requirement goes down, our water requirement goes down, and also very importantly, fly ash, which used to be a waste product few years ago, it is not the same today. So there are consumers for fly ash, and so it is kind of becoming a product which can be sold. So to save environment, save water, and to gain some value out of this waste material, we need to revamp our or troubleshoot our fly ash handling systems in the plants where there is a problem. And what we have come across, that there are many plants where the fly ash system is not working properly. The dry fly ash conveying system is not working properly. And today, the three speakers, including myself, we are going to address this very important issue. My name is Dr. S.S. Malik. Once again, I welcome you all to this presentation, to this webinar. And I am with me, I have the pleasure of having Professor Peter Whippich of University of Wollongong and Mr. Sanjoy Paul. My basic introduction is I am currently Associate Professor in the Department of Mechanical Engineering, Thapar Institute. For the last 21 years, I have been associated with bulk material handling. I used to work in power industry earlier, and then I carried out my master's and the PhD study from Australia. In our laboratory, we have conveyed over 40 different types of ash. Professor Peter Whippich was my PhD supervisor. He is still my mentor in many aspects of technical as well as personal matters. He is the director, he is a professor in the Department of Mechanical Engineering, UOW, Australia. He is a director of International Solid Handling Research Institute. He was pioneer in bringing the dense space pneumatic conveying technology to Australia. He has over 40 plus years of rich experience of carrying out 800 plus bulk solids industry projects. And he has done many ash projects as well, design and troubleshooting. We also have the honor of having Mr. Sanjay Pal with us. Mr. Sanjay Pal, I know him for several years, almost 20 years now. He is one of the pioneer in India in terms of, he's a very rare combination, I would say, his knowledge. He has designed 30 power plants, as well as he has been to the field in the way of commissioning 30 plus power plants. So this combination, I believe, is very rare. He is a very senior engineer in Development Consultants Private Limited, DCPL, as well as he used to be, he earlier, he had a long career in DCIPS, which is a sister concern of DCPL. He has also, he has almost worked with all the key suppliers of ash handling system in India. So he knows the different systems and their components very well. He has also got tremendous amount of experience with dry bottom ash handling system, which is typically supplied by some international players. For today's presentation, we floated certain forms, and we have got tremendous amount of response. Now, if you see that quite expectedly, almost 60% of the participants today, they are from the operation and maintenance department of various thermal power plants across the country. In fact, some are from international as well. We also have got senior management personnel from the energy sector. Also, about 10% of the participants are the designers and suppliers of ash handling systems. So if you add up all these, so you have about 73% of people who are very directly either designing or operating or doing maintenance or taking decisions in the area of ash handling systems in thermal power stations. I also welcome my colleagues from the researcher community, which looks like 3%, which is not a bad number. So welcome to all of you. This time we actually invited you to provide your issues, the challenges that you are facing beforehand. I'm very thankful to all of you that you have shared your views on that. We can see that most of the issue which is coming is there is an under capacity of ash flow. You see 30% in pressure and vacuum conveying. So ash flow capacity is not up to the mark, up to the required number. So 31% of the participants have responded to it. Second is ash conveying capacity goes down in the rainy season, that is 24%. So it seems like a I mean, there are quite a few power stations which are located towards the eastern part of the country, where even from the month of end of May to right up to September or maybe first week of October, we have long rainy seasons, and obviously they have this problem. Then also we have about 10% issues, rapid wiring, 16% to be honest, rapid wiring of the pipes, material handling valves, wiring of the same pipes and bends. So capacity issues are about 55% of the persons have raised capacity issues. Some people have, some of you have said wear issues. And there are also another very important issue is arcing and rat holing of the ESP hopper. So about 2/3 of the participants, some way or the other, are affected by low capacity issue of the ash handling systems. And then we have rest of it is other maintenance, wire issues, etc. So we are going to address all these issues. Myself, Dr. Ripich, and Mr. Paul, three of us in our respective domains, we are going to address these issues, or we are going to try our best to address those issues up to your satisfaction. A very brief introduction to our laboratory at Thapar Institute. So this is the pneumatic conveying pilot plant we have in Thapar Institute. This particular setup was, I'm very thankful to NTPC for setting up this big facility in India. In fact, this is probably the largest facility in the institute level in the whole of Asia. We have pressure as well as vacuum conveying system. Within our institute, we can convey up to 70 tons per hour of ash in pressure system. and 40 tons per hour of ash in vacuum system. These numbers that you have heard is correct, 70 and 40 tons per hour. For an institute, these are very big numbers, I understand, but this is something we have already achieved. So this is another view of our existing facility. These are some of our characterization laboratory. So we have a pneumatic conveying test facility, hopper test facility, as well as the powder characterization laboratory. Over the years, I have worked with many industries. Our research group has worked with many industries: NTPC, Tata Power, Reliance, a Belgium company, Granitude, OPGC, Aditya Birla, Airlock, Hindelco, etc., HPGC. But then in the recent times, we have moved from to startup, which is located inside the university, which has been set up by the approval of the director, Thapar Institute. And this is as per the policy of the government of India, that the faculty should take their research to the outside world to support the society and industry. So we have developed our company, which is located inside Thapar Institute. So through that, we are now doing most of the projects, commercial projects. So we have recently completed one project for one of the NTPC plants. And last year, we have done one project for KC Cottrell. So I'll come to that later. One of the things that we have done over the years, in the last 3 to 4 years, we have conveyed 40 types of fly ash in pressure as well as vacuum conveying. So we have got a very large amount of data of ash. And so we appreciate the variability that you can see in the ash. So we have conveyed air preheater ash, ESP first field ash, ESP second field ash. Of course, these are not from the same plant, of course, but we have very strategically selected plants, selected different ESP passes, ESP third, fourth, fifth, sixth, seventh, eighth. So from all the plants, all the fields, we have collected ash, buffer hopper, remote silo, etc. So 40 different ash samples that we have collected and tested, pneumatically conveyed in our pilot plant at Thapar Institute. So I personally have I personally have run about 3,500 to 4,000 ash conveying cycles. So that has given our research group a tremendous amount of first-hand experience of the conveying experience. That what are the things that you can do to increase your conveying capacity, and some of those we are going to share with you today. Now, one challenge that we must understand, that ash is not a single, it's not a very well specified product when it comes to powder technology. There is a tremendous amount of variation in ash. So you can see particle density based on our experience of conveying 40 ash samples. Particle density can vary from about 1600 to 2700 kg per meter cube. Bulk density about 550 to almost 1050 kg per meter cube. And the mean particle size also can vary from 40 to 190 microns. Now, this is based on the 40 ash sample data that I have just shown you. Now, what it tells you, that you can't have a single design for all these things. I mean, yes, you have to make it, but there is a challenge. Conveying 40 micron ash and conveying 190 micron ash, these are two different stories. And this is a challenge that all of us face. So I will come to this part later, that how we give a solution. I will come to that later in the part 3. So we understand, yes, there is a challenge of designing, conveying, operating at the plant. That's because of the variability of ash. That's one factor, of course. Also, there are many undersizing, etc. have been done. But but today we are not discussing what has been done and what is the problem. We are discussing about the solution. We are not discussing about the past. We are discussing how we can actually make an existing system work. We are very much aware that at this point of time, no power station is going to make a huge investment because of the because of the transition nature of the energy sector. So what is to be done, that we have to smartly extract the best out of what we have by making certain changes. Minimum intervention to our existing plants and see what we can do minimally and increase the capacity. So the way I have prepared my planning of the talk is like this. I'm going to pick up one topic. I'm going to tell you why this happens and what can be done to rectify the system. Okay, so that's how we are going to go. The first issue is pipeline getting blocked. So this is probably the worst way. Forget about low capacity. This means zero capacity. I mean, you don't get zero capacity as such, but you do have pipeline blockage from time to time. And this blockage tends to be worse in the rainy season, as I understand. Now, the basic reason for that is, the most obvious reason for that is insufficient flow of air, insufficient airflow. That's the most obvious reason. Now, if that is the case, then what is to be done? Obviously, the airflow has to be increased. Now, how airflow can be increased in the plant, that we are going to discuss in the session 3 with Mr. Sanjay Pal. We are going to come to that, but in this session, I'm going to say that for the typical vacuum system, there is a certain velocity requirement, and for pressure system, there is a certain minimum velocity requirement. Now, we do not use the term velocity while we design and scale up and rectify a plant. We check everything based on Froude number, which is the velocity divided by the square root of acceleration due to gravity g multiplied by the d, means the ID of the pipe. For vacuum, you need this number in the range of 12 to 16, Froude number. I think I missed to give the pressure reading. Hang on. For pressure, this will be from 6 to 8. For pressure, this will be 6 to 8. So for vacuum, this is 12 to 16. For pressure, this will be 6 to 8. Now, in vacuum, you might think that why we need extra velocity for vacuum. The simple reason is, in vacuum, the air is thin, density is low, below atmospheric density. So you actually require more. You require more velocity to compensate for that loss of pressure. At the end of the day, this is a game of momentum. And that's why in vacuum, you roughly need double the amount of velocity or Froude number to make the ash flow, to pick up the ash and to make it flow. Now, earlier people used to talk of velocities, but we don't do that. These days, we have got many experimental data to support our claim. We use a term Froude number because Froude number has diameter, pipe diameter into it, V by root GD. Now, why is pipe diameter important? The reason pipe diameter is very important is that if you look at how the ash actually flows in the line, it doesn't occupy the entire pipe diameter. So you see the top figure, the ash actually flows across the bottom of the pipe. Ideally, it should have been as per the bottom figure. That the most ideal situation would have been if the air could push the entire ash, the entire cross section of the ash. Now that is not the case. So only. So what is happening? Air is basically sliding over the bottom layer, non-suspension layer of ash. And because of that, the full strength of air is not being applied on ash. So only it is a shear effect which is actually pushing the ash or shearing the ash along. So therefore, and now, so what happens is, if the diameter increases, there is, I mean, compared to the amount of ash that you have, the layer that you have at the bottom, that amount actually increases. So what happens that it becomes more and more air actually bypasses that layer and goes over the top. So to compensate for that bypassing effect, you have to have the pipe diameter. And therefore, we don't use velocity, we use pipe diameter. The second important matter is pipeline getting blocked, but this may not be because of the insufficient air, but because of the wrong step-up location. Sometimes certain system suppliers, they have given too many step-ups. The 1 kilometer line, they have given 3 different pipe diameters. So that is 2 step-ups. Step-ups, why the step-ups are given? Step-up means increase in pipe diameter. Why are they given? They are given to reduce the pressure in the line, pressure drop in the line. But then if you step it at the location of step-up, what happens? You reduce the velocity because you increase the pipe diameter. By continuity equation, mass flow rate of the air is same. So if you increase the pipe diameter, the velocity is going to go down. So people want to control that velocity. They want to reduce the velocity because gas continuously expands. So you want to reduce it to a certain degree. But then if you give the step up too early, what will happen is the velocity might abruptly fall below the saltation velocity or the minimum transport velocity of the ash. And so you would start to get a buildup there. So for that, what is to be done is you have to remember that whatever number I set for pressure, say Froude number should be from 6 to 8, depending on the nature of the ash. So what I do is, or what is recommended is, in every step-up location, you actually increase the Froude number by 10 to 20% of the original Froude number. Because as you go towards the end of the pipeline, the air density goes down. And as you already know by now, that as the air density goes down, you have to compensate that by increasing the air velocity or the air Froude number. And the exit Froude number, in my recommendation, this should be at least 150%, ideally up to 200% of the initial Froude number. So if your initial Froude number is, say, 7, it should be at least 14 towards the end of the pipeline, around 14, 15. I mean, that's how I do the things. Right? So step-up criteria is very important. Don't give too many step-ups because you will start to get saltation in the line and pressure buildup and line choking. Then low ash transport rate. So one was the line blockage, and then you have low ash transport rate. This is because of insufficient airflow, conveying airflow. So what I actually mean is, let us now see, this is a diagram which is called the pneumatic conveying characteristics. So what I have in the y-axis is the pressure drop. What I have in the x-axis is the mass flow rate of air. You can see there are 3 black lines, continuous lines, 120, 100, and 80 tons per hour. These are showing you the different tonnages. Let us say I want to operate at 120 ton per hour, and I have demarcated a point, a black dot point, covered by a light bluish curtain. So that is my operating point, where the V3 line cuts the 120 ton per hour line. You can see that it's a sky blue shaded portion which is there. So let us say that should be my ideal point of operation. Now the question is, why that should be the ideal point? Why not any other point? If you look at these lines, these are typically fly ash lines. They have a pressure minima. So these, what we call, these are U-shaped line. So they typically have a pressure minima point. So you should try to operate the system at the pressure minima, where you can operate the system with the with the lowest air mass flow rate and pressure drop. If you do the calculations, you will get it like that. Okay, minimum pressure drop of air and a reliable mass flow rate of air, because you certainly don't want to operate everything at the blockage point. You need to give some margin for certain leakage or varying nature of the ash, etc. Now, if you have got an under capacity system in your plant, so what your supplier has given you, instead of that ideal pressure minima point, he wanted to reduce the compressor capacity, and instead of giving you that blue shaded line point, he has given you at a less mass flow rate of air, because you wanted to reduce that compressor capacity, obviously, for certain reasons. And so what he has given you the red dot point. Now the problem with the red dot point is that here, as you can see, that if you reduce the red dot point, if you simply go to the left horizontally, now you are below the 120 ton per hour capacity line. And therefore, your tonnage will actually get reduced. So let us say now it is 110 ton per hour. So a low capacity, if you just study the pneumatic conveying characteristic curves, the beauty of these curves is it tells you a lot of things. So if you decrease the airflow, your capacity is going to go down. Now the other extreme could be that you don't want to take a chance and you increase the airflow. Let us say, I mean, that's probably a very rare case in our country these days. Let us say there is a new plant coming up somewhere and you have decided, okay, you know what I will do? I will use a lot of extra air. I will have a lot of margins in my system. So what you have given is, you have given 10% extra air, and then whatever is the airflow on top of it, I mean, you don't get the exact compressor of that capacity. So you have to select the next available model. And so you get additional 5% capacity increment anyway. And so the air that you are actually drawing in the system or in the pipeline, that is far, far more than what is actually required. Now, intuitively, you might think that is fantastic, I have margin. But please understand that margin can be counter margin when it comes to pneumatic conveying. And that's purely because of the nature of the characteristic curves. So again, you see from the blue point, I have gone to the red point by increasing my mass flow rate of air. And what I have done, from 120, I have again come down to somewhere around 110 tons per hour. So this is what happens, simply characteristic curves. Also, compressor pressure is very important, and that's probably very intuitive. I don't want to spend much time on that. Obviously, if you don't have enough pressure in the compressor, then your capacity is going to go down. Just it will go down vertically. So here, the difference from the last two graphs and this one is, in the last two graphs, you have moved horizontally left and right, and you ran into trouble. If the compressor is limited by pressure, then also you will run into trouble. You simply don't have the enough pressure in the air. Sometimes I have seen people are very, very obsessed with the capacity of the compressor, flow rate. And they have a very chalta hai type attitude in terms of pressure. So people have given a lot of under pressure compressors, undersized compressors in terms of under pressure. And obviously, you look at the characteristic curves, from 120 tons per hour, you will simply drop to 100 tons per hour. So my friends, pressure is also very, very important factor in terms of operating your system correctly, along with your FAD of the compressor. So both are extremely important. Vacuum systems can be very tricky. I do not have a very large time to do this case study, but this is something we do when we have a face-to-face workshop running at Thapar. So sometimes what happens is, in a vacuum system, when the vacuum in the system starts to go up, say for example, you are getting certain blockages in the vacuum system, what happens when the vacuum of the system goes up, the air density goes down tremendously. And so your effective mass flow rate goes down exponentially. And as a result, you start to get further and further reduction in the airflow, leading to more blockages in the line. But one good thing I must say about vacuum system is it is kind of a self-cleaning system. In the pressure system, if it blockages and if you have too much fine, then cleaning it can be real hell. Whatever ash we have conveyed about those 40 types of ash, we have seen in the vacuum system, if you stop and start the system in terms of you stop the material flow, then start it again. So you give certain after certain trial, the system starts to run again. So you might think the vacuum system doesn't choke, which is fantastic. But again, in the plant, if you do that this auto start stop thing, I mean, which typically is already in the interlock, that if the vacuum goes up to a certain, say 350 or whatever, 375 millimeter mercury, the material outlet valve of the ESP hopper is going to stop. It's going to close. So you might think, okay, my system is running, it is not blocked. It is, I have the interlock. But then what happens, because of that many times start and stop, you are losing valuable time for conveying. So you are basically increasing your idle time. Now, having more idle time means having less effective time for conveying and having less achievable capacity of conveying. So you must provide sufficient airflow, and you must not provide more than sufficient airflow. So there is a very sweet spot in the car that I have spoken of. Low ash feeding rate because of insufficient blow tank aeration. This is one of my most favorite topic and most, I would say, ignored topic in the power plants. Very, very ignored. We often talk of compressor capacity, vacuum pump capacity, but there is a tremendous amount of opportunity which is there in the blow tank operation. By giving proper aeration to the blow tank, you can actually increase the capacity. How? I say that the compressor, if the compressor is your leg, the blow tank is your heart. So if you want to run faster, you need strong legs, that's all right. But first you need strong heart also. The blow tank is truly the heart of the system. And you have to understand one thing, that the ash by gravity will not fall in the line. This is not simple Newtonian mechanics. You have to provide certain air in the blow tank in certain way, and then only the ash is going to nicely fall. Most of the time people talk of compressor capacity being low. But then what are you going to convey if you don't have material in the line to convey? If from the blow tank or from the ESP hopper ash does not come in the line, then what are you going to convey? That is a very, very important point. Now you have to understand one thing, that a portion of the total transport air is going to the blow tank. You definitely take a tapping and send it to the equalization line. In many plants, you also take a tapping from the same supply and you fluidize the blow tank. Of course, in certain plants, you take a tapping from the instrument air. But you have to understand that some portion of the transport air actually goes to the blow tank, perhaps in the way of an equalization line or top air line. We call it top air. In the plant, many times it is called equalization air. Both are the same thing. Now, these equalization air and the fluidization air, they push the ash to come out against the conveying air and drop in the pipeline. Because at the bottom of the blow tank, you have pressurized air. So unless you push the ash from top by giving air, fluidization and equalization, the ash is not going to come down. As simple as that. Now, a portion is tapped from the blow tank air, fluidization and equalization. They are tapped from the transport air system. So if the transport air compressor is undersized, so less amount of air will go to the blow tank to push the ash down. And so the ash will not come down because you are not pushing it hard enough. So this is very important. So blow tank aeration optimization, you have to have the right balance of the top air, of the fluidization air, and of the conveying air. Now, I'm not getting into a debate here that whether the fluidization is taken from instrument air or from the transport air. That is a separate thing. But from wherever you have taken, the balance of these three is very important. Because what happens is, okay, I'll come to this first. What we have seen in our experience of those 40 different ash samples, of course, they behave little differently. And if you increase the fluidization air, you generally get very good amount of increment in the tonnage. But there is a particular limit. So beyond a certain limit, you don't get that increment, but it doesn't decrease also. So it remains there, stabilizes. But if you don't give any fluidization and you give some fluidization, 5% fluidization, there's a huge impact, huge positive impact that you can make to your system. Now, the reason for that is so that this fluidization air, you are not just pressurizing your blow tank, you are decreasing the inclined surface friction. The blow tank has two parts. One is the cylindrical part and the conical part. Now, in the conical part, there is a friction because it is not vertical. So the ash is sliding over that surface. Ash is sliding over that surface. So if you can, now what happens is, because of the friction on the blow tank, the tonnage actually reduces. Now, if you can, if you give good quality fluidization air, very measured, with a large on a large surface, what will happen? The rheology of the ash will be smoother. The apparent viscosity of the ash will decrease because ash is like a semi-fluid thing, and more ash will come in the line. Of course, too much ash is also a problem. I will discuss it later. And also pre-pressurization. So you have to maintain certain differential pressure across the blow tank. I will come to that later. These are some of the pictures that we have taken from a certain plant. These are, of course, top discharge blow tank. But you can see that the fluidization pad was very, very constricted. So there was not enough fluidization air which was coming in the top discharge blow tank. Now you have to understand, in the top discharge blow tank, majority of the air that goes to the blow tank, majority or all, is from the bottom of the blow tank, via the fluidization pad. So if the fluidization pad is not allowing enough air, or you have even less amount of air in the first place, so what will happen? The ash will not be agitated to come out of the blow tank, and so you will have problems. The ash will be there, it will not come out, and over a period of time, the pad is going to get entirely clogged by the fine component of the ash, and you are simply not fluidizing your ash, so your tonnage is going to go down drastically. The another important aspect that you have to consider, that fluid has got a property that it always tries to take the path of least resistance. This is very similar to electricity. Now, across the blow tank, there is a certain amount of pressure drop which is bound to happen. So your air is coming from the transport air compressor, let us say, and it has 2 or 3 paths to go. One is the conveying air, which is going from the bottom of the blow tank. One is the equalization air, which is the top of the blow tank. At the top, you inject that air, and you might have taken a tapping as a fluidization air, or you might have taken it from the instrument air thing. That's another story. But what will happen is, you think you are the air coming from the compressor. You always want to go through the least resistance path. Now, one path is through that blow tank. You have to go up and then down, and then you see a lot of ash, 4 tons of ash sitting there, or maybe 2 tons, whatever. And you have to penetrate through that, push it. The other way is you simply go through and through straight using the conveying air line. What are you going to take? Obviously, the conveying air path, that option, easy path. Like everyone does it. All my students do it. Always they take the easy path. I mean, that's probably very natural, isn't it? We all do it. So what will happen? Air is going to bypass that blow tank. And again, that's a big problem. As you already know very well by now, you already know it. that if I don't give enough air in the blow tank, the material is not going to come out. So what you have to do is you have to create a differential pressure across the blow tank so that air in the requisite amount, in the controlled amount, enters into the blow tank. So by giving a differential pressure, as you can see the red arrow in the transport air line, I have seen it, very surprisingly in certain plants, they give the DP in the fluidization and in the top air or in the equalization air line. So what happens is you have a very big issue. You have a big problem there. The problem is instead of restricting the conveying air line, you are restricting the top air line. So more and more air bypasses the blow tank. So what you have to do, you have to put a throttle, you have to put an orifice in the conveying air line so that some amount of air goes to the blow tank. And so we can actually calculate that DP specifically for the blow tank. So please understand, this DP would depend on the nature of the blow tank, on the size of the blow tank, on the type of ash. So this needs to be properly calculated. In the top discharge blow tank, another problem that happens that the riser pipe that you have very, very dense amount of ash coming through that. Because only a limited, maybe 30% amount of total air goes to the top discharge blow tank via the fluidization pad. And so what happens is you have 120 tons per hour of ash coming out, or maybe whatever number that is, but only with 30% air. And only when the ash comes out from the blow tank, then only it meets with the rest 70% of the air. So in the blow tank, in the riser pipe, which you can see the L-type pipe, the 90-degree pipe, there's a heavy concentration of ash. So with that, you will have very dense phase flow and you will have a lot of DP, lot of pressure drop across the blow tank. So the pressure drop across the blow tank in a top discharge pipe is always more. And once again, this has to be calculated, and an equivalent amount and the similar the DP, similar DP you have to drop. You have to make the similar DP drop in the conveying air line, and accordingly the orifice has to be selected properly. So these are small things. Orifice, you see, okay, it's a small thing, but it is controlling the operation of your heart. So that's you can't ignore that. One very important point is small blow tank size. Sometimes to reduce the buffer upper height and to reduce the overall size of the blow tank, sometimes I go to the plant and I see multiple small blow tanks. The problem with the small blow tank is that your number of cycle increases. When you have many small blow tanks, your number of cycle would actually would increase. Now in every conveying cycle, there is a certain portion, especially towards the end of the cycle, where the ash actually trickles. Initially, the ash will go very nicely, but towards the end of the cycle, the ash flow rate actually decreases. The other problem is there are many valve opening, then pre-pressurization, venting, etc. All those are idle times. So practically, you can't achieve something like a 20 conveying cycles per minute. I mean, we recommend 15, ideally 12 per blow tank per hour. But in certain plants, I have seen that the supplier has provided something like 20, 24, and so on. Now, if I have to operate with that amount of precision, then my blow tank, my system has to be as smooth as a Swiss watch. But unfortunately, Swiss watch doesn't deal with fly ash. So practically, it is not easy to do that. It is not possible. Nobody can prove it theoretically, but practically every power plant operator would agree with me perhaps that so many cycles per hour is not possible from a blow tank. So blow tank sizing is very important. So we don't recommend more than 15 discharge cycles per hour per blow tank. Now, this is a very important point, ash flooding into the pipeline. If you have a very free flowing ash, very free flowing ash, this is fantastic in terms of it will not have any ESP hopper blockage problem, no rat hole, no choking, no arcing problem. If you have very coarse ash, very free flowing ash, very low cohesion, that is great in terms of hopper flow. But what will happen that when you open the material outlet valve, let us say at the bottom of the ESP hopper or at the bottom of the blow tank, all of a sudden a lot of ash will come out. Now you have to understand one thing. If you have to convey in one pipeline 120 tons per hour of ash or 100 tons per hour of ash, whatever, if you have to convey that, you must feed the same amount in the line. You can't feed 200 tons per hour of ash and then ask your compressor, which is designed for 100 tons per hour of conveying. You can't ask that compressor to manage it. Likewise, the other thing is also, I'll cover the opposite part later. Now, typically what happens when you have multiple blow tanks, let us say 5 blow tanks, 4 blow tanks, all discharging simultaneously in a pipe. Let us say you have a 10-inch pipe or a 12-inch pipe, and every blow tank has a size of say 8-inch. So if you have 4 of those blow tanks, you might be actually feeding about 150 to 180 tons per hour of ash if it is very free flowing ash. And the conveying that you require, your compressor has been sized for 120 tons per hour. So that extra 60 tons per hour, what is it going to do? It is going to block the line, right? So synchronization of the feeder with the system is very important. Please understand that the synchronization is extremely important. So you need feed control. So what is feed control? What we say that if you have a very free flowing coarser ash, you must stop giving or give very low amount of equalization air. Any extra equalization air is going to cause a lot of flooding of the ash into the pipeline. Also give low amount of fluidization air at low pressure. Okay, so don't give too much extra air in the blow tank. That's the main thing. And you divert that extra air in the conveying. So you have to provide a lot of conveying air, but you reduce the top air and the fluidization air. The opposite problem is when you have extremely cohesive ash. I will take another 7 to 9 minutes to complete. So when you have extremely cohesive ash, then the opposite happens. The ash doesn't want to come out of the blow tank. That's another problem. Okay, there's the opposite problem. I mean, that's the beauty of ash. I mean, for me, it's a beauty, but for the people who are operating, I fully empathize with you. The problem that you face is very hard to control the ash, and you just don't know from how it is going to behave. So we have seen many ash samples which are extremely cohesive. They just don't want to come out of the blow tank. I mean, we know that the ash is there. I mean, we see in our data logger in our lab, ash is not coming out. It's just sitting in the blow tank. Now, what we do to run it, we have done many trials and we have kind of expertise on that. So in that case, we give moderate amount of top air, because with cohesive ash, what happens if you give too much top air, it is going to make the ash compact. So we only give moderate amount of top air on the lower side, to be honest, but we give high amount of fluidization air. So on the inclined surface, we churn the ash as much as possible. And we give a regular amount of conveying air. You don't have to give a lot of conveying air for these airs, but you have to provide a lot of fluidization air. A line getting pressurized, I go to the power plant, I heard this term quite often, line is getting pressurized. It took me some time to understand what it means. So it actually means is you have a shooting of the pressure in the line. So there is something called a steady increase of pressure, and there is something called a very kick pressure. This is a typical characteristics of the group B material. I'm not going to go in because of the lack of time, I'm not going to go in the diagram of this, but what you have is, you sometimes have very dilute phase type material. Means, typically if the ash particle size, probably I'm telling in a very vague way, but typically if the particle size say is above 100, 110 micron, And if it is sandy, that's very important, the feel of the ash, sandy, coarser, it's probably a group B material. Group B material means where you start to form slugs if you don't give enough air. And you know how you know that is happening? You typically have blockage towards the end of the pipeline. So typically near the vertical, you have blockage there. You sometimes have pipe vibration, and you have a rattling sound. It is like cut, 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 cut. You sometimes get this kind of sound when you have group B material. Now you would say, what is the solution? Solution is, if you have group B material, now you know the solution. You don't have to even ask me. The solution is, you don't pressurize your blow tank. You give very low amount of air in the blow tank with low pressure. Don't give too much of equalization air, too much of fluidization air. You need fine fit control and give extra air in the conveying. If you can't give extra air now in the conveying, at least you can do one thing. You can reduce the air which is going in the blow tank, and you because you need to, these ash is going to flood the line. I'm coming towards the end of my presentation. Ash is stuck in the ESP hopper. 10% of you have given me feedback that the ash gets stuck in the ESP hopper. Excessive, and this typically happens if the ash is very, very cohesive. So you have arcing problem. At the bottom of the hopper, you can see the ash has made a gain strength, and it has made an arc. Then you have rat holing problem also, where the bottom is open, but the ash is lying on the side of the ESP hopper, and they typically start to build in the edges, and then they occupy the entire hopper, unfortunately. And you have to understand, again, ash doesn't fall by gravity. So if I talk in very simple terms, very, very easy terms, so ash wants to come down with gravity, that's okay. But then you have friction on the wall, and you have strength of the material. So because of that, there is a resistance to flow. Now, for the flow to happen, the downward push, which we call the consolidation stress, or you can say very simply, where you can say that the gravity force must be higher than the strength of the material and the wall friction, which are actually counterproductive, which are working against the flow. Now, the situation is, if you have a certain ash and you already have got an existing hopper, ESP hopper or buffer hopper, and the ash is not going down, what can you do? One very good thing you can do. First of all, you see whether you are causing any blockage in the line. Maybe there is an adapter piece. Maybe there is a lot of hammer blow which has taken place. As a result, there is a sharp change. There's not a smooth geometry that you have in the ash flow line. The other thing you can do is, you can reduce the friction of the ash with the wall. How can you do it? You can provide more fluidization air. So you can have some fluidization pads, give sufficient amount of hot air so that you don't inject moisture. And you will definitely, we have done it with so many ash samples. This is brilliant. Invariably, you give a little bit of fluidization air again in the hopper, similar to blow tank, and you start to get a very good amount of ash flow. But then also you have to be careful. This is only good. Let me again tell you, this is only good if you have a cohesive ash, which is not falling otherwise. If the ash is very flooding, coarse, group B material, you give this extra fluidization air, and it is going to, too much ash is going to fall. And again, as I said, the synchronization is very important. So you may not be able to synchronize. You might be feeding too much ash. One problem that we have found in the vacuum system, what happens is, when you start the vacuum system, it immediately sucks ash which is directly above it. And so what happens? It just sucks it out, and then the rest of it consolidates. So we have seen it. You can see the certain pictures. So we have put a camera inside our hopper that we have inside in our laboratory. So we have got a laboratory which can hold something around 1,000 kg of ash, 2,000 kg of ash, and we have run the system, and we have put a camera inside on the top. And what we have seen is, the moment the vacuum system starts, it just sucks everything from the core, from the center, and the ash on the side remains as it is. This happens, of course, for very cohesive ash, not for free flowing ash. And then, what we did is, I asked my colleague and my students, do one thing, just switch on the fluidization air. So we have fluidization pad in our hopper. The moment we switched on, the rat hole actually collapsed, and we started to get good quality flow. You can also make certain changes in the ash intake valve. So if you are unable to break the arc, maybe temporarily, I underline this word, you can close the ash intake valve setting, create extra vacuum in the line, and you can break that arch. But don't leave it like that. Make sure you come back to the original air setting, because if that point is very constricted, you will actually have a lot of high vacuum in the line, which is not good for a consistent operation. This is good for temporary, once or twice, if the ash is not falling, if there is a broken ash in rat hole needs to be broken. So this is how you can do it. So I'm coming to the end of my presentation. So my recommendation would be, do not see the system and the component in isolation. The system and the component both have to work simultaneously well, and then only your entire system will work brilliantly. It requires quite a bit of understanding, quite a bit of technology, understanding of the powder flow, testing facilities. You should test your powder to understand, to do proper diagnosis of the root cause. That is very important. You don't do a surgery without first understanding what is causing the problem. So first is you do the diagnosis, and then you do the surgery, and which is basically the troubleshooting at site. We'll cover that towards the end of the the session 3. We're going to cover that. All right. So with that, thank you very much. Now we'll move to our very eminent speaker, Professor Peter Whippich. I'm now shutting down my part of the presentation, and I would request Professor Whippich to take over. Thank you very much.
Well, thank you, Dr. Malik, and good morning, ladies and gentlemen, and greetings from down under. I hope everyone's keeping healthy and well. Very interesting talk, Dr. Malik, and I will be following on related aspects to that talk. I'm looking at the time now, and I'll try and condense my presentation as much as I can. But of course, here we're looking at the focus of increasing ash conveying rate in thermal power plants. And my presentation today is going to be a bit different than previous ones. I thought it'd be appropriate to really provide a bit of a checklist of important issues that need to be considered when tackling this topic. So the first half of my presentation is going to be quite boring. I apologize for that. It's going to be a lot of text, but it's going to hopefully cover some key issues that we need to think about. So hopefully everyone can see this and hear me. If not, someone can jump up and down and let me know. All right, so to properly explore the options to increase capacity, we need to firstly understand and quantify the problem. So quantification is a very important first step, and quite often a difficult step. And then we can try to understand and identify the root cause or causes of the problem. So first step, quantification, understanding. Second step, try and look at the root cause or causes of the problem. And then a process of elimination may be needed for the purpose of a root cause analysis, and then also establish and prioritize appropriate solution options. And this is important because quite often there may be a number of solution options to consider, and they can vary a lot in time needed and cost. And there may need to be some band-aid solutions needed initially, and then you get some justification to move to the next stage. So, so quite often it can be quite a complex consideration. So what I'd like to do here is to describe firstly some of the more common root causes of capacity problems, and I'd like to highlight that I'll be focusing on blow tank systems. I'm not covering any of the vacuum part that Dr. Malik's already covered. And then also share with you some possible solution options. So with problem quantification, this I find a bit of a frustrating issue. So I'll just, again, summarize some of the key comments here. So the key parameters for designing and operating troubleshooting systems, I'll run through this fairly quickly. So we've firstly got the conveying air mass flow rate. And so that's MS, mass flow rate of air, kilos per second. This conveying solids mass flow rate through the pipeline. All right, so we're talking about pneumatic conveying through a pipeline. There's also, that's related to system capacity. But here we're just I want to identify what MS is, and that's the product flow through the actual pipeline in tons per hour. And then there's the conveying pipeline pressure drop across the entire pipeline, delta PT in kilopascals. Now, of course, MS is determined or required by the plant as determined by the coal properties, the flow rates through the plant and so forth. And the air mass flow rate is needed. That's the critical design parameter from a design perspective to achieve the required MS through the pipeline to give us the system capacity we need for that given product and pipeline or pipeline combinations. There may be different lengths involved for different silo destinations. And then pressure drop is an important parameter too, but it's really a byproduct of conveying particular ash through a particular pipeline at a particular airflow. And the other thing I'd like to highlight too is, so some designers like to focus on the solids to gas loading ratio, or M-star I call it, and they use this for design and troubleshooting. And really, M-star also should be considered as a byproduct of reliable and efficient transport. That should be our priority. Once we achieve that reliable and efficient transport, whatever the tonnage is and the airflow, then if we're achieving our objectives, then M-star really is considered as a byproduct. Anyway, so really out of all that, we can summarize that the two most important parameters for pneumatic conveying are the air mass flow rate and the tonnage through the system. Despite this, most pneumatic conveying plants do not record or quantify the air mass flow rate or the actual conveying rate through the system. So they don't use airflow meters, for example. They don't have load cells. Mostly they don't have load cells on the silos and blow tanks, etc. So this information is very hard to come by, and they tend to be the most important parameters. So it's a very unfortunate situation. We do have some plants use pressure gauges or pressure transmitters and record that information over time. They do that from a control and operational perspective. So we can go into the control room and probably try and extract some of the information. At least that's something that we can get, all right, fairly readily in some plants. So it's possible to quantify maybe your conveying pressure, your supply pressure. There may be a pressure gauge on the air receiver and these sorts of things, or the outlet of the compressor. And in some plants, you may find a pressure gauge on the blow tank, which is also useful. But don't ever trust a pressure gauge. The first thing you do is tap it and make sure it works. And the second thing I would always do, put quick connect couplings in there so that you can always take it out, put a new pressure gauge in there and make sure that you're getting the same reading. And of course, if it's different, then you have to see, well, if the first one's wrong or the second one's wrong. So it's always an issue that we have to check. So don't ever assume a pressure gauge is reading the correct value. But anyway, once we get our pressures confirmed, and if we can record that off a data acquisition system, say through some sort of control system on site, then that sort of pressure history is very useful indeed. It gives us an idea, a picture on how the system is performing. So to estimate or quantify the air mass flow rate for an ash handling plant, we quite often have to rely on compressor specs. So we also have to check that the compressor is running as per the specification and no one's fiddled with it, or they've changed the gear ratios or something like that. So there's a few checks that we have to make as well. And this is useful information, particularly in India, where they use what I call low pressure transport air compressors, where all the air is used by the compressor, supplied by the compressor has to be used. We can't throttle the airflow through a regulation system. So relying on the compressor specs, that's useful as long as we make sure that the compressor is running at the right speed and so forth. And so then we know what the total airflow is going through the pneumatic conveying system. But it doesn't give us any information or detail on the distribution of air, like Dr. Malik showed, how much air is going into the conveying line, how much goes into the blow tank and so forth. And And as Dr. Malik indicated, that information is quite important. And I'll come back to that in the more detail with some pictures. But as I said before, I warned you before, I'm going through a lot of sort of checklist information here. So to quantify and estimate your tonnage through the pipeline, we have to rely on plant information, equipment data, and so forth. We look at the blow tank volume, the dimensions, the cycle times. We look at the ash properties, bulk density and those sorts of things. And the only area usually in a plant we can get some idea of system capacity, perhaps on the outloading rates, how much goes out in trucks or train or slurry pump or whatever. Sometimes that is recorded in total terms, tons per day or something like that. So that gives us some indication of tonnage, but that's for the entire plant usually. And then we have to try and break that down into the pipeline, what's happening. So that's where we have to rely on all this other information. So as a result, it's difficult to determine the control airflows and actual tonnage through the pipeline. And these happen to be the two most important parameters for pneumatic conveying. Now, we can look at putting airflows and meters, airflow meters and controllers on the system. And these are expensive. Not many people do it, but I do suggest for managers, if they're listening, consider this as an investment opportunity, an investment strategy, so that we can then look at using this equipment to optimize and reduce your air usage and power usage through your plant. Now, we've been quite successful in Australia in doing this, and we're using this working with partners in China. And there have been cases in some power plants we've been saving up to 30 to 50% of power and air usage through a plant. And this is, so with the initial investment, you get payback within several months. So, this is something you need to think about for the future. And it's definitely, once we have that information, we can then really look at in detail and more accurately what's going on in the system. So let's look at common root causes, capacity problems. So we have ash properties, of course, where my experience is that, once the power plant is built, ash properties, the specs can be quite different from the contract stage and design stage. So then everyone's finger pointing and there's all sorts of arguments going on. And also over time, things can change. The ash properties can change, even, changing your ash extraction collection method can change your average ash properties. Segregation within the plant can change your ash properties, even from blow tank to blow tank. And of course, if you change your coal supply, that could change your ash properties. And power demands vary too. If you're going 50% capacity, depending on demand, to 100% capacity, then your ash properties can change too. So there's lots of ways we can change ash properties. And this is something can be like a chasing your tail scenario in terms of trying to lock down what your ash properties are, because they keep changing. So we have to allow for that in our design and our consideration and understanding of the plant. So the second area is blow tank design and aeration, and Dr. Malik has already talked a bit about that, but I'll talk about different aspects of that. And then there's blow tank operation and cycle times. That can be an important issue for capacity problems. Pipeline design, Dr. Malik already touched on that, and the importance of stepping your locations to achieve optimum operation. Air supply plant, very important consideration too. And finally, your filter and bag house could have an impact on ash capacity as actually it hasn't been sized properly. And particularly if your ash properties change, your filtration efficiencies may change, and suddenly you're overpressurizing you get dust emissions, and then people have to start cutting back. I've seen that happen in some places. Anyway, so I only have time to talk briefly about ash properties and then blow tank design and operation. So quickly, so the important properties we need to look for here from a pneumatic conveying perspective is the size distribution, your particle density, and your bulk density. There's many different definitions here, and I won't go into the detail of that. My experience actually generally has a relatively wide size range, so you can get some sub-micron particles up to, depending on your ESP, your field, and all that sorts of designs issues, you can get up to millimeter size particles. So it's a very wide size range of material, and those sorts of materials can segregate very easily when you start to handle them. So the particle sizing can change a lot due to what I've mentioned before, if you change your collection method. And I've seen people do this in power plants, you know, how they collect the ash, they change the sequencing, and suddenly the ash properties are different. Also in a power plant, the big silos, and you've got some fluidization at different times, that can change your sizing of what actually comes out from blow tank to blow tank. So, you know, even from a dense phase perspective, I've seen this happen where, you know, the first one or two blow tanks have got coarse ash in them and the system blocks. And then once they get rid of that coarse ash, and there's fine ash predominantly coming out of the silo, it's due to segregation, and then it conveys quite nicely. Anyway, so with such variability, one way to avoid that from a conveying perspective is to go more dilute medium phase if you can afford to increase the airflow. So generally, when you've got if you can't avoid this variability, then you do need to think about looking at a medium phase flow as opposed to a proper dense phase system. The other thing that Dr. Malik mentioned briefly, I'd like to focus on that too here. Coarse ash can also display very free-flowing and flooding characteristics. And also these sorts of materials de-aerate very quickly along the pipeline. So these sort of products, you need to keep them moving at all times. Because if for some reason, even for a few seconds, if the air is turned off or reduces in the pipeline, the ash can deposit out very quickly. So this is very important when you consider changeover of blow tanks or pipelines, so that you make sure that whatever ash is moving in there, you get rid of that before you do any of these changes. All right, because otherwise you can, even for a few seconds, that's enough for that product to deposit. And then the next time a batch of ash comes through, it will block the pipeline. So as a result, blow tank design operation need to be considered carefully when handling such floodable materials. Now, the second aspect I'd like to cover is blow tank design. There are many, many different types of blow tanks out there, different designs, the methods of air injection or blow tank aeration. I'm referring to the same thing here, or they're all different designs as well. So each blow tank design and aeration method that you have has its own set of advantages and disadvantages. All right, that's important to understand. So really, I said one of the key steps is understanding, and when addressing these sort of capacity problems, we need to understand the different blow tank designs that are out there, their characteristics, how they perform, their advantages and disadvantages, and so on, so that we can then select the best design and an appropriate method of aeration to suit the product properties, the product variability aspects, as I've described before, and the application conditions and requirements. All right, so that's a very important, this understanding I mentioned before is very important step in this whole process. So we also need to select quality components to suit the product and application conditions in terms of, the ash can be very abrasive, very gritty, can get into very small crevices, if you like, seats and seals and O-rings and stuff like that, can rip them apart very quickly. Temperature issues too, so ash can be quite hot. So we need to make sure the components we select, because they are quite often the weak link in the system. They're the small things that can make a big difference to an entire plant. So we need to make sure that you get the right components matched to the product and application. So the other thing that quite often people, and Dr. Malik touched on this, is how can we control blow tank discharge rate? And so I thought I might go a little bit left field here and talk about that issue separately. So with blow tank discharge rate, here we see just a typical bottom discharge blow tank. On the bottom there, we've got a fluidizing discharge cone, and I'll come back to that a bit later. But it's a fairly simple system. We only look at one blow tank at this stage. So here we've got our air mass flow rate, and I'll only consider steady state conditions at this stage. And so there we've got conveying air down the bottom there on a mass basis, MFC, and then we have our aeration air. And then we have the airflow coming out, air mass flow rate. So under steady state conditions where the pressure in the blow tank is constant, the air mass flow rate into that system equals the air mass flow rate coming out. So where the air is distributed between the aeration and conveying line, that can become quite important for blow tank control and discharge. So then once we maybe pre-pressurize and let it go, the mass flow of solids as indicated here. So very simply, just to simplify that diagram, get rid of all the valves, etc. So this is what we have from a mass perspective, mass flow rate into the system and out of the system, and the mass flow of solids out of the blow tank. So we call that the feeding discharge rate, and then that becomes, of course, the conveying rate. Now, a few important comments. So one way to increase the mass flow rate here for this system is to increase the proportion of aeration air to conveying air. All right. So if you're restricted by the amount of pads that you have and the design of pad, that will limit the amount of air you can put through those pads at any one time. Then what we have done in the past, you can increase or install an extra aeration line in parallel with the main blow tank aeration line. And this can maybe go through some sockets above it. That's quite good. But you also need controls on that. Otherwise, you don't know where the air will go. So you need to be in control of all this. That's very important. So for low pressure systems, which I will generally, my experience is in India, most of the pneumatic conveying systems, the positive pressure systems are low pressure. Transport air compressors, sort of maximum 200 to 300 kPa. I call that low pressure. Most of the systems in Australia are high pressure, 600, 700 kPa. And in China too, they tend to be 500 to up to 700 kPa gauge compressors. Anyway, so as a result, and there's reasons for that, and I won't go into the detail of it, but as a result of using these low pressure systems, these airflows I've shown you here, MFA, MFC, MF, etc., are all subsonic airflows. So that what that means is, if you know anything about fluid mechanics, you only need change to resistance somewhere in each of those lines, and the airflow will change quite easily. So those airflows are dependent on whatever resistance or back pressure can be seen in each of those respective lines. So when you initially pressurize, you discharge, and end of cycle, those resistances will change, and who knows what those airflows will be, how they, in other words, the aeration air, which is important here to achieve a certain discharge rate, will change during your cycle. And so really, to ensure that you've got the correct aeration, amount of aeration with respect to your conveying air, you really need to have good controllers, airflow controllers on your respective lines. And quite often what we're finding now, people are being convinced that we need to put some sort of flow meters in there as well. And that's what's been happening in China. We've been optimizing a lot of these plants with smart control and moving towards artificial intelligence. And really to have any chance of doing that, we need to quantify the problem. And to do that, we need airflow meters. And so, as I said earlier, to the managers that are listening, consider this as an investment opportunity to achieve optimal operation for your plant down the track. All right. Anyway, so moving on. So there are other ways to achieve and control your mass flow rate of solids, especially for your coarse floodable materials. We can go for top discharge systems or side discharge blow tanks, and I'll show you examples of that later. We can also, from a bottom discharge perspective, make sure that we don't use a too bigger outlet valve. So we we select the correct size of outlet valve to give us the flow rate that we need, or limit the flow rate. As a band-aid solution, we've done this where some products drop into a 12-inch line from something like an 8-inch outlet valve or 10-inch outlet valve, and with a floodable material, the product is out of control. And so you can put an orifice plate in there. You can do some calculations to work out what size you need, and that sort of limits that flow rate, that flooding capability. So it's not the ideal solution, but it's something that you could to get you out of trouble, and then look for better longer-term solutions. Something that we have done, and to some success. In some plants, I've seen solids flow controllers used on the outlet of blow tanks, like a modulating valve that you can see here. For ash systems, I just wouldn't recommend this. These will get ripped out in no time. But something that we actually had in our first blow tanks we installed in our laboratory back in the 80s, we used a cone dosing valve. This was developed by the Germans for underground mines, and we used it for pneumatic conveying systems for above surface sort of mines, applications, I should say. And the cone dosing valve is not an on-off valve, it's just a flow rate regulator. And so this cone dosing valve oscillates, goes up and down. You can adjust the frequency with the control box at the top here. You can also adjust the amplitude. So the beauty of this is you can link that control box to your conveying pressure, and if the pressure starts to rise, which it could indicate deposition and potential blockage in the line, the cone dosing valve can oscillate and be pushed downwards. So what it does, it restricts the flow of material into the line, and then and it's all done automatically. So when if the pressure then starts to come back down again, it can lift back up again. So it's a proper regulating valve, but it will wear over time. It's not in the high velocity area. It doesn't really shut off the flow where you get high velocities there. But it's just enough to slow that down a little bit. So if it wears a little bit, it's not a concern. You can actually, it's self-adjusting, as I said. So it's an interesting invention. We did use it a lot. But these days we don't tend to use it. It seems to, for many standard pneumatic conveying system, this is a bit of an over sort of complication. But actually you can see here the first blow tank in our lab is the one on the right, which I'll come back later. And that has got a pneumatic logic controller, which is as mentioned earlier, for underground mines. So there's no electrical components here. It's all done pneumatically. And that's got the cone dosing valve there. And the one on the left has the electric box in there to do the same purpose, to control the frequency and amplitude of the cone dosing valve. When we did so-called normal blow tank discharges, we just take the cone dosing valve out and then we operate it like a normal blow tank. But anyway, just interesting how these were the first designs that were installed in our lab. All right, so the other issue, I'll just quick comments about feed point. How are we going here? Yeah, okay, look, I will just quickly say here, it is a physics problem, right? So it's a physics problem. So we've got a mass flow of solids going vertical down into a pipeline, and personally, I prefer dropping product into an established airstream. A lot of systems don't, and then you don't know what's going to happen. But here we've got a certain mass flow of solids against a certain mass flow of air. But it's a physics problem. It's actually a momentum balance problem. So if you consider the mass and or the density of the product and its velocity, that's momentum. And once you have a certain feed rate and it coming out at a certain velocity due to gravity, then you need a certain momentum of air to balance that, to make sure that you can move that product in the direction that it needs to go. Otherwise it'll block. So, and if you have more product coming out, so if you've got a coarse floodable material, the only way you can really balance that is with air momentum. And the only thing you can really adjust in a lot of these pneumatic conveying systems is the velocity of the air. So it's a physics problem that we're dealing with, and it involves a physics solution, physics-based solution. So, and once you get your head around trying to understand what's going on with a lot of these things, it helps a lot to work out what's the best way forward. Anyway, so very quickly, top discharge blow tank, fluidizing pad at the bottom, aeration air, discharge out through the top, all right? Not suitable for cohesive powders, because fine cohesive powders where you get channeling inside the blow tank. And also if the product's too heavy or coarse, it won't come out. So it's got limited application, but in the right area, you know, if you've got a group A material, 20 to 50 micron ash, top discharge works fine. And also if you've got a coarse floodable material, sort of D50 of the order of 100 to 200 micron, which is a group B material, then the top discharge also limits the discharge of that material. So it's a good way of controlling or limiting that discharge rate. So if you're looking at like a top discharge system now, as opposed to an individual blow tank, we've got the same features here. Now we can see the conveying air line. There's your feed pipe. There's a product coming out of there. Where it combines as the feed point, and there's your conveying pipeline. Okay, So the simplifying those various flow paths. So we've got the conveying air at the top here, your blow tank aeration air, and your conveying air. So MF, what goes through the conveying line is the addition of those two airflows that I mentioned. So that blow tank aeration air does depend on your powder properties, your pad design, and pad material, and the required feed rate that you need. And the feed pipe is an important consideration for these types of blow tanks, because the feed pipe is an actual pneumatic conveying pipe that needs to be designed properly. If not, you can get blockages or plugging occurring in that line, and that will restrict your blow tank discharge capacity. The other consideration too is we're lifting the product against acceleration due to gravity. All right, so there's a lift loss involved here. So if you look at the pressure required from the inlet to the outlet of that feed pipe, that could be 10 or 20 kPa. And I can tell you now, 10 or 20 kPa means a lot for these so-called low pressure systems. And it can make the difference whether you get that tonnage or not. So that needs to be allowed for properly in your design. All right. So just again, it's coming back to understanding all those key issues and differences of these different blow tank designs. So with bottom discharge, you're discharging with gravity. That's an advantage. So here we've got the conveying air from left to right. We've got the blow tank aeration air, in this case through a fluidizing discharge cone. There is some additional hoses that you can see there that they weren't used, they weren't needed. And here we got the discharge going in the direction of gravity. So we don't have any feed pipe losses here. So we do have that bit of saving, if you like. But the other issue to consider here, of course, is if you've got a coarse floodable material, we have to, as I've mentioned before, we've got to take some care. Anyway, so your gravity, acceleration gravity helps discharge your solids. These blow tank systems can handle a wide range of products from fine to coarse with a limit, as I mentioned before, about floodable products. What we've found, the fluidizing discharge cone helps to maintain a consistent discharge rate, and particularly for fine powders. So that's a good feature. And I'll share some research results if I've got time a bit later on. But for these floodable materials, unless you restrict the outlet and take some extra precautions, you have to take care with floodable products. You may need to limit the outlet size. Another sort of compromise is what we call a side discharge blow tank. So we've got the fluidizing pad as the top discharge, and the blow tank aeration air, conveying air from left to right. And here we've got the discharge of material. It lifts a little bit inside the tank, and then it goes into the main conveying pipe and discharges out through the right. So that's why we call it a side discharge. These blow tanks in some ways are similar to top discharge if you've got fine cohesive powders that can channel. So we have to be careful with that. But for coarse flooded materials, if you like got economizer ash or air heater grits and stuff like that, which can flow very quickly through a bottom discharge, well, this will help to limit that. So these are quite good. These side discharge blow tanks are used a lot in China, for example, for these sort of coarse floodable materials. Fine ash can still flood the pipeline for these blow tanks, so be careful with that. So if you imagine dropping fine fluidized ash from above, which is, the ash is aerated and it's hot, and it dumps into the tank, it can run out into the pipeline to some distance out to the outlet valve, no problem. So you could start off with a full block of ash in your pipeline before you turn the conveying air on, and that could cause some problems too. So we've got to watch that. But the amount of lift here is very small, so your feed pipe losses are minimized. There are other designs available, like this one here. This is sort of technically as a side discharge, but it's probably got more top in there than side. And these are quite large tanks. So we've got a blow tank aeration through a series of pads, as you can see there. And then the product is discharged, and it meets up with your conveying air line a bit downstream. And if you look closely here at what's happening at the inlet to the feed or discharge pipe, you can see here, they've got a 10-inch pipe here. This is quite a big system. And I started scratching my head. Your product's got to be, it's got to force through this little hole or this gap down the bottom there, it's only about 50 millimeters high. And so this system, I forget what it was, 100 or 120 ton an hour. And if you did your mass continuity on that, your velocity needed here is several meters per second, and it's not possible. And so you've got to watch the gap there to make sure it's sufficient to give you the discharge feed rate that you need to achieve your system capacity. So that small thing that you see there, that small gap, seems to be a standard gap used by this particular designer or manufacturer for all their blow tank sizes. And that small gap can be enough to restrict the capacity of the entire plant. Anyway, moving on. Some innovative blow tanks we're involved with. Haven't got time to show too much of this, but horizontal blow tanks for low headroom applications. So you can see there, this is for a tandem application. And this was a system that the client wanted to upgrade because they didn't have enough capacity. They wanted to get an extra 30%. They were prepared to increase the size of blow tank, pipeline, etc. Anyway, so we ended up going through the problem of or the issue of quantification. As I said before, it's one of the first steps. So how do we determine the performance of the system? How do we verify those numbers? And there's no load cells, tonnages. The issue is real in ash handling plants and many pneumatic conveying systems. So we ended up using some sophisticated 3D CAD modeling techniques and modeling the angle of repose and what effect that had on your batch capacity and hence your system capacity. So for a low angle repose of 5 degrees, you can see there we would get 1.56 cubic meters of product in that tank. And this actually, the tonnage of this particular product was about a ton a cubic meter. So that's about 1.56 tons. Then with 20 degrees, you got 1.2, and 30 degrees, you got less than 1. So you can see how just the angle of repose can make a big difference on how much product you get into your blow tank. And these are nice blow tanks. They've got air slides on the bottom. They discharge out as an air slide, but we have to be because it's horizontal, the angle of repose can make a big difference to how much product you put in there. So in the end, we ended up developing a program that can apply to any blow tank system. And you can, if you can do your angle of repose testing in the lab, then you can do this quite accurately. And then you can model your system, quantify it fairly well, a lot better than what we just picking numbers out of the air. In the end, we achieved our objectives, a 30% increase by just improving our cycle times on their system. And the client was very happy because they didn't have to they just had to buy some airflow meters and airflow controllers, and they got their 30%. So they were very pleased. How much? Oh, how are we going? Yeah, okay. I'm just looking at the time here. Sorry about this. So method of blow tank aeration is very important. We did a lot of research on this years ago. I'll try and finish in 5 minutes if I can. And we did dilute phase investigations, fluidized dense phase, and also single slug. So I won't talk about single slug. That's not relevant here. I'll talk about dilute phase and fluidized dense phase. And so these are the two blow tanks I showed you earlier. We took the cone dosing valves out. So we had a conventional, just single point injection aeration system blow tank. That was the first blow tank that we had. Then we installed one with a fluidizing discharge cone as shown. And so the whole point is to do side-by-side comparisons. And we wanted to check feeding efficiency, system performance, side-by-side, up to 100 meters, up to 300 meters, 500 meters. So we, long distance pipeline that we had in our laboratory. And to kind of say, blow tank 1's the original one. Blow tank 2's got the fluidizing cone, as you can see here. So blow tank 1's just single point injection, and you can see the fluidizing cone there. Got the same capacity and same outlet valve, same pipeline, etc. So it's a valid side-by-side comparison. Anyway, so we tested ash, fine, coarse. We also tested pulverized coal and cement. And just to summarize some key results. So the more cohesive powders, we had problems, always problems with blow tank 1. We had rat holing, channeling, had stuff left behind. So this was a problem. The discharge rate of all the products, even the free-flowing stuff, the discharge rate decreased in the second half of the discharge cycle. So it's due to funnel flow effect out of that hopper. Once we used some top air, 10%, 20% top air, we found it compacted the powder because these powders are compressible. And with a bit of top air, it compacted it and exacerbated these problems. It made the whole thing worse. So with a lot of fine powder systems, we tend to use fluidizing cone air only. We do some makeup air, as I showed you before, with an extra aeration line, but we tend not to use any top air. For blow tank 2, it's fitted with the fluidizing discharge cone. All the powders, the fine stuff, the coarse stuff, all discharged evenly and consistently to the last drop of product in the blow tank. And so for the entire discharge cycle, it was linear, straight, right down to 0. And we, as a result, we got much better system capacity with the fluidizing cone system installed. We've got 20% more capacity and then blow tank 1. And also our air usage dropped by 20% using the fluidizing cone. So with the same amount of air, we saved air by having more efficient blow tank cycles. And so then we got rid of that first blow tank. So blow tank 1, then we fitted a fluidizing cone, and that became our test rig for many decades, as you can see here, with windows on there, with lights, so we can actually see all these rat holes and things occurring inside the blow tank. I'm sort of running out of time here. Blow tank operation, yeah, some important issues there. Look, what I'll just a couple of interesting things. I'm not sure how much of this is done in India, simultaneous blow tank discharge. So here we actually we've got the conveying air from right to left. We've got actually 8 blow tanks that discharge simultaneously at the one time. So it collects all the ash from the whatever field this is, 1, 2, 3, or whatever, and it all simultaneously discharges. So we have aeration on the bottom there. These are side discharge blow tanks. And so if you start to look at this system, looking at simultaneous, we have done simultaneous discharge in a lab and monitored some of this in the field. And some very interesting things happen. We find generally that the mass flow rate in the first tank is higher than the subsequent tanks because the first tank discharges into an empty line, the second one got ash in it, et cetera, et cetera, et cetera. So, you know, if you want to try and get even discharge out through all the tanks, you may really need to adjust your aeration rates. So the blow tank at the end may need to have a bit more air than the blow tank in the beginning. So, but I'm not sure how many people do that. I think they just let the whole thing dump out and hope for the best. But that means your tonnages vary a lot through your line. So if you don't allow for that in your design, you may have trouble with your air velocities. So because the air flows through here do change due to the blow tank aeration being added into your simultaneous discharge blow tanks. So these are things that need to be checked. Again, it's understanding and quantifying all these issues so we can design and operate our plants properly. But this seems the way that things are going in China. This is one system I would not recommend, where they just have these tanks at the bottom. These are bottom discharge blow tanks, and there's no aeration there. It's asking for trouble. So when you fill up your blow tanks, there's no pre-pressurization on these. Ash goes in, it runs out in the line. If you've got a good ash, yeah, you'll get rid of it. But if you've got a coarse ash or a bad ash, it'll all block up, no worries. And here again, you've got 8 tanks that simultaneously discharge at the same time. So here, when it starts to pressurize, actually a lot of your conveying air is used to pressurize the tank. So you will lose some of your conveying air just to pressurize the tank. So this is becoming a very complicated blow tank feeding system. All right, anyway, so in conclusion, so I think I did take time. So and just a few quick comments to make. Despite apparent simplicity, blow tanks come in very different sizes, types and arrangements, and numerous components and methods of aeration available for blow tank operation. It's essential to match the blow tank design and its components and a method of aeration to your material properties and your application requirements. And once properly selected and operated, your blow tank systems can perform reliably and efficiently for many years and with little maintenance. So thank you for that. Sorry if I took a bit longer, but I think I was pretty much on time. So thanks very much, and I'll hand it over to the next presenter.
Okay, thank you very much, Peter. We always learn something or the other. I found some incredible clean power plants. I mean, that's probably the highlight. And
Okay.
also, we have once in a power station, we actually measured that different airflow going to the equalization line or top line, fluidization line, and conveying line. And it keep on, it's a transient flow actually, it keeps on changing.
Yep, I agree with that.
Yeah.
To try and control that, that's a next step. Measuring is one thing, then controlling is another thing.
Yeah. So now we are in the third session of our webinar. And Mr. Sanjay Pal, I hope you are here.
Yes, I am here.
Okay. So I have the honor of introducing Mr. Sanjay Pal once again. He has more than 30 years of experience in ash handling and cement plants design, as well as installing, commissioning, PG testing. And he's also not only with dry pneumatic conveying systems, he has also worked with optimization of ash slurry system and dry bottom ash handling systems. So he has a very large experience of DC, IPS and DCPL of over 30 years. Mr. Pal, we welcome you to this webinar.
Thank you.
Thank you for having the time to join us today and enlighten all of us with your practical engineering and plant design and commissioning experiences. So this is a slide I had shown before, this pie chart. These are the topics that our audience, our participants have raised before coming to this webinar. And I believe many of the topics we have, Professor Vipich and myself have already covered. So those we are not going to cover, but there are certain topics, more practical topics, where we definitely welcome your input. So let me start with some of the wear issues which our presenters have, our participants have raised. That wearing of the pipeline and the bends in pneumatic conveying line. So this seems to be an issue with quite a number of participants in their plants. So what is your recommendation on that? What is your thought on this? I mean, how can this be solved?
Good morning, all of you. So first of all, their question is the erosion of pipe and bend in pressure conveying system. If the main thing is that the ash is a very corrosion and erosion prone. They used to provide more erosion and corrosion to the material they touch. So what happens if, suppose in the flow, if the velocity is too high, if the impingement of the ash particles is very high, and if the flow is not smooth, then at any portion, at particular point or particular region, these ash particles hit very hard and the erosion takes place. Somo?
Yeah. So is there, so what the plants can do, Mr. Pal, like if they're having too much of erosion?
So one thing is the velocity is to be controlled. The easy way to control it is to make a step up to reduce the velocity so that impingement does not take place heavily. But at the same time, if you put the step up, then it is to be looked whether the line blockage does not happen, because if velocity reduces drastically and it is less than the velocity required to flow the provided ash as per the ash material, as per the ash particle density, the other characteristics of the ash, then it may try to settle down and block the pipe. So optimization is to be done, and this is to be carried out in a very judicial and strategic manner. So
Right, and also after the bend at strategic locations, the reinforcement is to be provided. So there are certain primary and secondary wear zone which needs to be identified, and in those locations extra reinforcement is to be provided. Okay. Thank you, Mr. Pal. The second question is material handling valves. I believe probably it covers both the vacuum and the pressure system. So some plants are having problem with rapid wearing of this valve. So what is your thought on this? How can this be rectified?
Actually, whenever you are conveying ash through a pipeline and valve is there, it is a tendency of the ash to settle between the seals. The gap in the seal, the edge of the valve generally sits when it is clean. But when it is not clean, when it is open, some ash gets deposited in the gap. So the second time or consecutive time when the valve tries to sit in the seal, the seating is not proper. The edge of the valve is not this disc is not properly sitting into the seal. And what happens? The erosion start from the edge. And generally, what happens when you provide any valve, they have certain material of the plate and SS plate, certain thickness and certain hardness. This hardness is to be ensured properly throughout the this valve plate. Now what happens? Many client which I have seen, they initially when the valve has a shelf life in the ash line. When it is being exhausted, it is being eroded, they replace it with another valve, but from local manufacturer who assure of the quality dimensions, but this hardness and the quality of the plates and the seals are not proper, and that increase the frequency of erosions and replaceability of the valves required time and again. The seal is to be replaced time and again, in spite of it is between some certain the interval of time, and that's why we provide replaceable seal with certain hardness, smooth finish, in both pressure and vacuum lines. So actually the plant user should point out whether the seal is to be replaced in proper time or not. Preventive maintenance is required. So
Yes, and there's one issue which seems to be bothering many people, and rightly so, is the in the rainy season. There is a capacity decrement. I mean, I understand probably there is a capacity issue throughout the year, but it increases in the rainy season. And of course, like I talked about the cohesive ash, and of course, like we have seen also that with the moisture, the ash becomes very cohesive, and we do need extra fluidization air in those times. The blow tank aeration is very critical. But is there any engineering way of? I mean, I know it's a thermodynamic thing that the moisture is going to drop, and because of this, after the aftercooler, you have bare pipes. So, is there any I mean anything that is can be taken at the design stage or in the maintenance by the maintenance team? What is your take on this?
actually, in the airline, in the Indian context, what I want to add is that there is a tendency in the winter season as well as in the rainy season to drop the temperature. Surface temperature drops, and when surface temperature drops, obviously the air intake which is being used to convey, there is a high moisture content, and moisture cannot be properly reduced, because some plant do not have proper air drying plant or may not have air drying plant existing for the ash conveying, or the air dry this silica gel or other things, decantation. What are the things they does not clean the air properly? The engineering stage, what can be airline, if it is being laid at a certain slope, suppose 2-degree slope, then what happens if any droplets of the water is being precipitated at the bottom, then it will flow in the slanted portion, and strategic points air the water tapping valves and draining valves may be provided. This is number one. Number two is that sometimes by heating. Now the heating when we are providing fluidizing air, it is being hot, and when the ash is coming, it is hot. But while flowing and while coming in contact with the cold pipe during the rainy season, the temperature drops. So intermittently, some heating arrangement is to be provided so that the moisture does not get precipitated, and the dew point, the temperature is above the dew point and flow is proper. So more.
Yes, and you know,
and also I want to add is that in air receiver, which I have found in the air receiver, the drain valve, auto drain valve does not work properly. So this area needs to be properly maintained, because when some water get precipitated in the air cylinder and this drain valve does not work, auto drain valve does not work properly, this moisture carries with the air. So this area is also to be looked into. So,
and in you know, I wanted to ask you, because this question, I mean, some people have already you know, asked me last week, you know, from a certain plant actually, that we are now giving troubleshooting services to the plants. We have already done it for one of the NTPC plants. So one natural question, you know, that is there, that you know, ash utilization is also a very important aspect. So can we do troubleshooting? I mean, to what extent we can do troubleshooting without stopping the power plant?
look, without stopping the power plant, we can do.
I mean, without stopping the ash handling system.
Yes, that is without stopping the system, the things can be improved. Things can be improved to some certain extent, based on the practicality of the situation. Number one, we can increase the airflow. We can increase the airflow. How? Suppose in every plant there is some standby equipment, compressor or vacuum, which is already connected with the air supply, but with some isolation valve. We can use that one both for pressure and for both vacuum. But here one thing is to be noticed very carefully. Suppose you require X amount of air, your compressed air, the existing compressed air compressor has a capacity of 0.8x. So if you add two compressor in one line, opening the isolation valve, then what will happen? The airflow will be double, but the requirement is the x, and you are providing 0.8x into 2, that is 1.6x. It will decrease your flow. It will not increase your flow, it is decrease your flow. So the standby compressor is to be used in such a manner that your flow range remains within the reliable capacity, that is 0.95 to 1.05 of the required amount, and so that you can tune it. And we can tune it with the ash variation, as well as arrangement with other arrangement which to be done in such a way that you make all this capacity measurement, capacity bleeding, tuning without shutting the plant. Then you just open the isolation valve and connect the standby compressor or vacuum pump with the existing line. This is one way.
Right. So, you know, it's not a one way. It's not a highway kind of a thing. You know, that you just go in one direction. You know, you have to hit that sweet spot. That's the most optimum point.
Yes.
And that's where technology comes in to estimate that point and then act accordingly.
Nextly, suppose you want to increase the fluidizing air flow. That you can do from outside, or you can decrease the if it is very coarse material, then you can decrease the fluidizing airflow from outside. No, you need not to be touch the system, and besides, there are a number of blow tanks will be existing in a standard power plant. So you can isolate any one of the blow tank. You do the proper things, proper modification as you need, and you connect it with the system. So there is some problem in the plants that all the blow tanks are not being properly designed so that it cannot be isolated by manual way. In that case, only in that case, proper design, proper shots of proper equipment design, proper isolation valve design, measurement with measuring all these things is to be done beforehand. When there is a annual plant shutdown or half yearly month plant shutdown, in that case we just place the isolation valves below the blow tanks on in the or in the other area required and open the isolation valve, let the system running properly, then one by one we can isolate the blow tank or other system and can do modification and join with the system. With this, the system will not hamper and the flow capacity will be achieved better. So
Okay, thank you, Mr. Pal. And now, we are just a few final thoughts. I have already mentioned we earlier I used to provide industry power plant solutions or general industry solutions as an isolated faculty as a consultant. But now with the government of India coming with the startup policy, we have already set up our startup technology transfer company within the university. And this is known as BSII, Bulk Solids Innovation India. And I'm very happy to share with all the audience that our company has recently received its second installment from the government of India to promote our ash handling technology into the for the benefit of the power stations. So government of India has also recognized this area, and they have provided us grant in support in terms of certain seed funding to BSII, our technology transfer company, so that our engineers can go to the plant. And it is a seed support, of course, but it's a good start, I would say. So I welcome the government of India, METI government of India for this support. So we provide troubleshooting solutions. We have recently provided solution in the first stage to one of the NTPC plants. And we are looking forward, we are getting many such calls from other plants as well. And we are looking forward to take you out of this painful area. If you contact us, we will be very happy. We are very keen to provide you this support via the technology transfer partnership from the university, and take you out of this very painful area. We all appreciate that. So your job is to generate power. Our job is to give you a system which would generate you the power. So that this is our expertise. Troubleshooting, design and troubleshooting is our expertise. And if we combine our strength, if you are interested, please let us know. We have already done it in one of the NTPC plant, as I've said, and we certainly like our Indian plants to be operated without any trouble. And in course of time, we certainly want to expand in other areas of power technology, nationally as well as internationally. And we certainly like to see that we can generate clean power. So that's the ultimate aim. And the way we actually go about the solution is in three very simple steps. First is step number one is inspection. So we make site visits, we collect plant data, assess problem. Second is we take certain ash samples and convey in our laboratory at Thapar Institute. So the whole work is done in collaboration with Thapar Institute, BSII in collaboration with Thapar Institute. We from that we design, we scale up, we identify what is the root cause. So this is basically the diagnosis part. So diagnosis is very, very important. So you have to understand what is causing you trouble. Once you quantify everything and you understand everything properly, then you can provide a recommendation. So in the first stage, we do the site visit, testing, modeling. This is all the diagnosis part. The second part is after diagnosis, then we do the treatment. So for the treatment, I mean, I'm just speaking like a doctor. and medical doctor rather. So for the treatment is, then the second stage is depending on the what is the problem, specific solution is provided to the plant. So our solution is not a generalized solution. Our solution is very tailor-made, customized for your plant, for your existing system, your ash. And we always have one motto in our mind fixed, which is we have to give you a solution by doing minimum intervention to your existing running plant. So we know how to do it. We don't beat around the bush. We go straight to the point based on our 20 plus, my at least 20 plus years of experience in this area. And the other advantage of that we are benefiting from having this technology transfer startup is people, very experienced people like Professor Peter Whippich, Mr. Pal from time to time, many other people. Also, there are many other experienced people are willing to help us through this mechanism. We have all so we can now depute people at site. We have done it already in occasions. So we have our complementary expertise and strengths to provide you the right solution that you require to make you run the plant without one less worry in your mind, which is the ash conveying problem, which is a big worry. And of course, being part of the university, we constantly develop new technologies. So we are a part of the innovation ecosystem. So right now we are making a method of a new novel kind of a coating, which is going to hopefully it will stop the this moisture ingress issue. The moisture in not only ingress, the moisture dripping out of air issue in the winter, in the rainy season. So some of my students are working to develop the technology, and our endeavor is, our attempt is to make it up and running by the end of April, so that before this next monsoon comes, we have this solution ready, reliable solution and affordable solution. That's what my students are working on. So we are now having the perfect platform to develop technology continuously, upgrade it and take it to the market. So with all your support and all our joint effort, I think we can make a drastic shift in the way ash handling in the way the ash handling is being conveyed. Ash is being conveyed in this country. So thank you very much. We are overshooted the time by 5 minutes. And I thank Professor Peter Whippich for staying with us on Saturday. Thank you very much. It's always indeed pleasure talking to you and learning from you. I still continue to consider myself as your student. And very many thanks to Professor Mr. Sanjoy Pal for coming to us on Saturday. Mr. Pal is our well-wisher, our startups well-wisher, and he's part of our bigger team also in certain ways. Thank you for sparing your time and sharing your knowledge with us. I thank all the participants to continue to attend our webinar series with a lot of enthusiasm. So your participation and the numbers in which you attend gives us continuous motivation to carry out our webinars, to share our knowledge with you. I look forward to talk to you. I look forward to receive your feedback, and all of us are very eager. If you have any problem in the plant, if any challenges that you are facing, you require a solution, please pick up the call, phone, or drop me an email at ssmallik@thapar.edu. That is the email I use for most of the time. Please drop us an email and we'll take it forward from that. We'll try our best to solve your problem. Thank you very much. So I'm closing the session. Thank you.